than traditional wooden doors, but also have an insulated core. The final design of our doors is the use of birch as our material and a 1/4 inch thickness. Moving on to our windows. Vinyl wooden frames are usually the least expensive choice, and they are suitable for many applications in office buildings, but wooden frames generally cost more than vinyl. However, wood has natural insulating properties and the appearance is better looking. A single pane window has a single pane of glass in each slot. It is the most affordable type, but allows for plenty of heat transfer. A double pane window dramatically increases a window's energy efficiency. A double pane window is sealed with an airspace between that creates the insulation. The thicker the airspace, the higher the insulation. Our final design of our windows is a wooden frame made of birch, single pane, and a 1/4 inch thickness, similar to the doors. Now I will pass it on to Alexis to talk about the design challenges in HVAC.
Where'd she go?
Frozen again.
Okay, let me share my screen. How do I share my screen? Share screen.
You can share it, right?
Brenda, could you pull up the slides instead?
Okay.
Great. Thank you.
Can everyone see me now? Can everyone see?
Yeah.
Okay, so we are next. Windows. Okay, here we go.
All right, so yeah, the AC system allows us to condition the temperature of the building or select rooms to the range of thermal comfort. A little bit more context, ASHRAE defines thermal comfort as when an employee wearing a normal amount of clothing feels neither too hot or too cold. To give it a numerical boundary though, OSHA recommends 68 to 76 degrees Fahrenheit for office buildings. So this is the range that we are shooting for. In order to achieve this, we're going to be using dampers to modulate the airflow so that we can control how much of the building we want to condition for optimal efficiency. And then we're also going to be using airflow sensors and thermocouples to work in conjunction with the dampers. The thermocouples will be able to measure the temperature and inform our control system. And then the airflow pressure sensors will give us pressure and velocity data to tell us how much air is going where. Next slide. Now, here's the design layout for our HVAC system. We've created this layout because it reduces the number of bends, overlaps, and long lengths of duct in order to decrease the pressure loss as much as possible. So that would hinder our ability to be able to deliver conditioned air to each room. Next, Eduardo is going to talk about the simulations we have run on this design and how we are using that information to further improve the system.
So in order for us to take in consideration how much CFM we need per room, we have to look at how much power the light bulb can dissipate, which at maximum power is 25 watts. So for our minimum CFM, in order for it to stay within the range of thermal comfort for humans, our minimum will be 5.5 CFM, which the average temperature is at 76 degrees Fahrenheit. For maximum CFM, that we could still stay in the thermal comfort is at 12.3 CFM at 68 degrees Fahrenheit on average temperature. On the screen, you will see a simulation at 10 CFM. Where on the left, you have velocity of the fluid, and on the right, you have the temperature throughout the room at 10 CFM. The average temperature at 10 CFM is 70 degrees Fahrenheit. where it still stays within the range of temperature of human comfort. Next slide, please.
Oh, can you
Quantum simulation is on this floor. It's coming from the AC unit to this floor of 100 CFM throughout the floor. Brenda, do you know why it's not playing the? Can you play it?
Oh, oops. No, I don't know, Eduardo.
Oh,
Do I have to click on it? Oh, here it is. Sorry, there it goes. Should be playing now. Cannot play media.
Is it okay if I share my screen?
Yeah, let me stop my share.
Thank you.
Uh-oh, that was working for us 5 minutes ago.
I know. Maybe it's my computer because I do have a Mac.
Yeah. So like I was saying, so the following simulation is of 100 CFM on the room. I'm sorry, on the floor, and on the left we have the results where it's each CFM for each room from 1 through 9. As you can see from these results, 7 out of 9 are having the same the CFM needed to stay in the thermal comfort of humans, except for room number 4 and room number 7, where we can say that our design needs improvement due to maybe like friction in the pipes or too many bands or the length of the piping. We could also control the CFM with the dampers shown in this picture. Next slide, please.
Oh, you're controlling it.
Oh yes. For further analysis for the heat transfer, we could use the concept of conservation of energy, where we could use thermocouples in the inner walls and the outer walls, and a DAQ to read the temperatures. For heat transfer scaling, this has been one of the biggest challenges in our project scope, but we could achieve this by Farrell's law of conduction, where if we achieve the same temperature difference in our model and the real life model, we could find the real life values by researching them, and our values for our model we could do experimental, and what we're looking for here is the power input that we need for our light bulb, so we could use it in the real life scale.
Okay, so our electrical design objectives. A general plan for a control system contains characterization, which is the generation of a measurement, monitoring, which is assigning a parameter range, and control, which is generating a response based on the two above. Our goals will be the temperature acquisition for data, generating a source, and airflow, which is our HVAC system. So this is system architecture, in which the environment communicates with the control system based on an input-output interface and sensors. Some of our system design considerations is we have a real-time operation where our environment is communicating directly with our control system, and we have to generate a response based on this is all going on in real time. So based on that, it affects our sensor selection and our hardware selection, and then our control software, what we do decide to use. Next slide. So based on that, we decided to go thermocouples for our sensors, pressure sensors. So the data acquisition device is actually going to, its control function is going to be generating a digital signal from an analog signal. And same thing with the microcontroller. Our blue is going to be generating a digital signal from an analog. Our data is basically its physical parameter that turns into an electrical, and we have to process that. So once we have that, we have our data, and then that goes into our control system, which is our lab view. And then the Palolu has, it's pretty flexible. It has different functions. So now we have to generate a command. So that's going to be a digital signal. And based off of that, our governing parameters, which is our temperature, we're going to be able to control, basically, we're going to provide HVAC, which is cooling, or heating, which is going to be our heat source generation, which is going to be done through relays, and a light bulb. So basically that light bulb is going to be creating a heat source electrical energy. So we have entire system that has two basic functions. We're satisfying data collection and control. and they're all communicating together. Next slide.
Oh, the summary. Yeah. All right. So to summarize what we talked about in this presentation, we gave you a little background on our project and our purpose for it, why it's sustainability. Then we went over the scope of our project and the project requirements that laid out the different goals we need to hit. After that, we talked about the technical side of our project, which included the building design, the air conditioning, and then the electronic system. So we do want to say that due to the current pandemic, we had to change course and we'll have to wait until summer to build our test bed, but we're still planning to move forward with that. And we'll return to campus when possible to physically build and implement our system and fully outfit it with the control system. All right, and then next one. Lastly, the team and I, we want to thank all of the people who supported us and made this project possible. Thank you to everyone who's here attending and watching. We want to, first though say thank you to our advisor, Dr. Pacheco. He's really, the person that created this project. He's, super devoted to it, has helped us tremendously, and also has been able to get us funding for it, which has been really amazing of him. We also want to thank all the senior design advisors, Mike Thornburg and Chris Bachman. You do way more work than you're compensated enough for. I really appreciate everything you guys do and for giving us this opportunity. And then we want to thank Dr. Curtis Wong from the Electrical Engineering Department, who helped us with the electrical side, because the 5 of us are all mechanical engineers, so we definitely needed help with that. And he was super kind and gave us a lot of great advice. So, lastly, we just want to say thank you to our sponsor, NSF CREST, who through Dr. Pacheco was able to give us funding. Thanks everyone for attending, and do you have any questions?
Okay, well, thanks team. So we do have some time for questions, about close to 10 minutes anyway. Does anybody want to go first? If not, I'll get it started. If we could turn to chart 15, I have perhaps a simple question. The one before this, I think. Oh, this one's okay though.
Sorry,
The question I actually have is just the way that you're reporting the CFM. Is that the amount for the scale model or for the full size room?
This is for our scale down model.
Okay. So this is for the scale down model. And
yeah, this is for our model. Yes.
Okay. Then how do you account, I guess, was that later on, I guess you talked about scaling things up, but I wasn't sure if that was this piece or not. When you've got things like the air friction and the pipes and all of that, how do you account for that as you scale things up to 12 times as large? Because obviously the material properties of air aren't changing.
Yeah, I can answer that. That's definitely the biggest challenge we have. I will say though, it's not the perfect answer to your question, but it isn't entirely in our scope to be handling all of the scaling, because that will come with the research to be able to, in order to figure out the scaling, it'll include validating the results from the experiment and comparing it to real life. But we have tried to do some dimensional analysis, like the one example Eduardo showed, where we're using different equations like Fourier's law of heat conduction, and in order to find what those scales look like. As more specifically to the air friction and pressure loss, that's definitely something that's pretty difficult. So we tried to compensate for it by designing a larger system so that our piping is a bit larger in comparison than it would normally be in a building, in order to try to reduce the amount of friction loss. But there's only also so much we can do with that. And so we did a couple things like choosing a round duct design that also reduces friction loss, and also, you know, it's made out of PVC, so it's really smooth. But we'll definitely have to be able to figure out the specifics on how things are going to be matched up, which we can do once we have, you know, real data in order to validate our results.
Okay. Other questions? All you have to do, unmute, be sure and unmute yourself before you ask your question.
I want to ask a simple question. I don't know if it's related, but nowadays, you know, air quality is a big issue. For example, you know, having like airborne viruses or something. So do you guys have any idea like how you can control the air quality into your ventilation system, like installing a filter or something like that?
Yeah, so I mean, this isn't necessarily entirely our project, but if you do want some information about that, you can install higher grade filters. They're called MERV filters. Something like MERV 13 is going to block out a lot of viruses, and definitely is going to make your system have to run a lot harder. But also another thing is there's a lot of standard designs that we use in hospitals in air conditioning in order to separate the airborne viruses from returning back to the rest of the hospital. So typically what you can do even in your own home is to have the air going from a sick patient's room directly outside, so it's not going back into the system as typical systems do. And then there's also some, you know, extra things you can do, like creating negative pressure loss that'll make sure no air leaves the room, it'll you know, like through the door, but only air comes into the room. And so that negative pressure means that it's a lot less likely for it to escape.
Oh, thank you. And congratulations. It was a great presentation.
Oh, thanks, Onyx. Thanks
Thank
so
you.
much.
Other questions?
So I have a question, Mike. So this is Chris. Thank you guys. Obviously put a lot of work. It was cool to see it come together. I was kind of interested in, you had kind of your pipe network, and you were mentioning that one or two of the rooms seem to be getting more flow into them than the others. I want to see, did you guys have any idea of maybe why that was, and what would be maybe some of the first things you try and change in order to get them to be the same as the others?
So the one that is receiving the most flow is number 4, which is this one. And that will be, I believe, is due to the backflow of the bending. Here, before it reaches the bending, there's a backflow. So I believe that's why it's getting more flow, more CFM than other rooms. And then the one that is too low, which is 3.2, where it's out of range as well, it's this one right here. And I want to think it's because the velocity is not enough there. And then once it turns here, it reaches momentum again, and that's why the CFM comes back up, and the velocity at the last one just speeds up.
Yeah, I'll add on a little piece, which is that it's definitely a problem that I think we're still trying to work through, and that we are able to reach air to each of the rooms, which is great, but we're also trying out another design to see if it's better. You know, we're initially going with this design because it's more conventional in the industry, but for, you know, realistic purposes for a test bed, we are trying something else that'll be able to bring the air in. There's a couple of things that really impact the system, which is one, you know, our level of CFM. So, you know, the more air we have have going into the system, we could definitely get more air into each of the rooms just by like forcing the pressure through. The problem with that though is then we have more turbulent flow, and that creates a lot more, a lot of issues. So we're trying to navigate a balance and how we're going to do that. And then the other part is also, just as, talking with Mike about earlier, is that, we do have a lot of, friction and pressure losses. So we also might return to this original idea we have of even increasing the size larger so that more air could flow through, not lose as much pressure, and it also would able to be more laminar. And then one of the kind of last pieces is just that in this simulation, it's not including the dampers we have. And the dampers are really what's going to be able to also modulate the airflow and be able to sort of make all the rooms a little bit more equivalent in terms of how much air it's getting.
Yeah, sorry.
No, that's right. No, I mean, that totally makes sense. Yeah, but you're going to say something, Eduardo?
Yeah, well, I was just about to say that all the dampers here are open, and our main goal is to reach a certain amount of balance in mass flow rate in each room when all the dampers are open. So when we're trying to pretty much reach another CFM, we could close it and then kind of reach more CFM in other rooms. But the goal is to balance the mass flow rate in each room when everything is open.
Yeah, very cool. No, makes sense.
Thanks.
Yeah, good working.
Any more questions?
Okay, well, thank you all very much. Congratulations. And for everybody, the next electrical or mechanical engineering presentation today is at 4 o'clock. But there's also computer science and technology presentations this afternoon. So welcome to Expo, and we'll see you at the next presentation. Thank you.
Great. Thanks, everyone. Have a good one.
Yeah, have a nice day.
Okay. Okay, well, let me go ahead and welcome everybody for attending the 2020 Capstone, the virtual Capstone this year. This is the 3rd day of presentations. There's about 100 presentations all in all between electrical and mechanical engineering, computer science, technology, and civil engineering. Most of the electrical and mechanical ones are in the subsequent days. I think that you're the 4th or 5th team that's presented. The teams that have presented ahead of you, I think, have done a great job. So perhaps it was those that were the most prepared that signed up to the early slots. But they set a high bar. Hopefully, we'll continue at that kind of quality level. We'll ask that one of the students take over the screen so that they're going to flip through the charts. We'll have time for you to introduce yourselves. We expect the presentation to take about 20 minutes, and then we'll be followed up with questions and answers and questions and other things. There will be a presentation following this one. So at 4 o'clock, we'll need to, at 4:40, we'll need to shut this one down and start a new one. Okay. Any questions before we get started?
Nope.
Okay, so whoever wants to take over my screen has the right to do that.
That'll be me.
Okay, excellent. Okay, Lewis, do you have you've got the screen?
Yeah.
Okay, so go ahead and start. Or
Okay, we're okay to start?
yes, please.
Okay, so good evening. I hope everyone has been having a good day so far. To start, my name is Brian Smith. For the Team Senior Design Capstone project, we were working with the Aerospace Corporation where we designed a universal test platform for commercial off-the-shelf COTS electronics radiation testing. Next slide, please. This is an overview of our agenda. I'll be introducing the team and talking about the overall pragmatics, which consist of the team's problem statement and project organization. Louis Tepox will be going over the technical progress with greater detail of the system design, requirements, deliverables, and a brief introduction of the data control and acquisition part. Marvin Sotero will elaborate more regarding the team's approach of utilizing low-cost test hardware, such as the Digilent Analog Discovery 2 module. Following this, Marvin will discuss the team's software design, software, flowchart, test analysis, and test plan. Edgar Palapa will discuss the transmission lines, which consist of the hardware overview and the use of buffer boards. I will talk about the team's design of the device under test fixture, which consists of the DUT and PCB design. Hugo Morales will discuss the radiation test setup and DUT fixture assembly. And lastly, Marvin Sotero will conclude our presentation with the team's overall progress. Next slide, please. So the team was divided up between two sub-teams, Edgar Palapa and Hugo Morales, who oversee the transmission lines, which consist of data transmission, testing, and integration. Louis Tepox and Marvin Sotero oversee the system design and data acquisition and control. I myself handled the design and implementation of the device under test, which is our DUT. Our advisor for this project is Ann Nye, and the company liaisons that supported us through this whole process were Allison Yarbrough and John Scarpula. Next slide, please. So as we all know, companies want to fly more and more non-military commercial off-the-shelf devices that are being used in small sats and CubeSats for space applications. Components such as A to D, D to A converters, clocks, FPGA, microprocessors, memories, and microcontrollers. The problem is that radiation testing is always needed when sending these COTS in space. Expensive infrastructures need to be fabricated and are customized to test these COTS, which involves high NRE. One way is to adapt vendors' demonstration boards, but they are not always available. We know that DACs need digital words, which require more components. However, we cannot put these components in a radiation chamber. The solution that our Capstone project will provide is a more flexible means to test these COTS by developing a mixed signal test fixture that contains the hardware and software that can exercise these COTS under radiation. The picture below displays that these demonstration boards are not suitable to be placed in the radiation chamber. Additionally, the Aerospace Corporation wants us to separate these COTS parts by using test electronics to drive signals for these COTS through cable lengths of up to 50 feet and frequencies of up to 50 megahertz. Next slide, please. And I will now pass this on to Louis to go over the technical progress.
Thank you, Brian. So in this diagram that you see, this is basically an overview of a system block diagram. The system consists of three main components. At the data control and acquisition, a PC will be programmed with the Digilent Analog Discovery 2 module. This module will send 3 signals through cable lengths of up to 50 feet and frequencies of up to 50 megahertz. With cabling of this length, we need a buffer board with a positive 4 voltage and negative 2 voltage rail to rail in order to drive these signals and provide enough power to the duct. At the device under test, the component will be tested until failure. Once the component has reached failure, this process is repeated using multiple DAC components. There are some requirements we must follow when implementing our design. The transmission digital frequency must run at 10 megahertz, but through analysis, the team saw that the frequency goes up to 100 megahertz. The transmission line length must be 10 feet since we need some distance between the setup of the radiation chamber. Inside the radiation chamber, the device under test fixture must handle ambient temperature, in other words, 25 degrees Celsius. And according to the data sheet, the fixture can exceed this requirement and is able to operate at 125 degrees Celsius. The transmission line bends must not exceed 6 bends since it can cause unwanted noise. But through inspection, the team saw that this did not affect our design and we had more than 6 bends. The duct fixture dimensions must be 10 by 10 inches. The duct component user replacement is to provide a dip socket to do multiple testing that the team implemented on the brass board. And lastly, the automated software test control and acquisition must run, pause, stop, test, and save data. And the team verified that the software implemented to our design allows us to have these parameters. The deliverables we must complete at the given deadline are the PDR project report, which was already completed, test software, device under test fixture design, and the final project report. The team tracked all the parts through an inventory spreadsheet and will return to the liaison at the Aerospace Corporation. Now, Marvin and I will talk more about the data control and acquisition for our design. The Aerospace Corporation provided the team with a device called the Analog Discovery 2 that satisfies the data control and acquisition requirements for the 12-bit DAC 7311. The DAC 7311 will be our device under test, and we must meet the requirements this device needs to make our system functional. The number of inputs the DAC has are 3 digital inputs, sync, clock, and data, and 1 output, which is an analog signal. And this device runs at a frequency up to 50 megahertz. The 82 has 16 digital inputs. The number of analog inputs and analog outputs are 2, and runs up to 100 megahertz, which satisfies the requirements for the DAC. This gives us an advantage since it satisfies the requirements needed and can also receive and send both analog and digital signals. I will now pass it on to Marvin to go into more detail for how exactly we will control and acquire our data.
Hi, everyone. So the software that's paired with the Analog Discovery 2 hardware is known as Digilent Waveforms. The Digilent Waveform software is instrumentation interfaces that we utilize to carry out the design for data control and acquisition of the device under test. We're the scripting tool for writing a custom test bench, pattern generator for playing, pausing, and stopping the tests, a logic analyzer for verifying that the proper data control was being executed, and the oscilloscope tool was meant for acquiring data for post-test analysis. Next slide, please. So the JavaScript test bench we designed using the Digilent Waveform script tool, set up the 3-wire communication signals and initialize signal frequency, most significant bit, select low, number of bits per digital word, the clock's phase and polarity. Then called on the Digilent Waveforms pattern generator tool to drive the 3 digital signals from the Digilent Analog Discovery 2 hardware from its digital output pins. The result shown by this slide here via the Digilent Waveforms logic analyzer tool was a 3-signal bus that matched the timing diagram under the device under test
quote unquote programming the DAC 7311 section of the data sheet. Our design for acquiring the output, if the COVID-19 crisis wouldn't have held us back from doing further testing, was to utilize the oscilloscope tool to log the 12-bit analog voltage read. Next slide, please. So this is a breakdown of our logic flowchart for our software. The data control and acquisition software was partitioned into 2 test routines and one post-test routine analysis. The first test routine, the .test setup checkout routine, verifies that the device under test is functional by sending out 3 initial digitized signals and logs an error if it is not functional. The second test routine, the device under test radiation test routine, exercises the device under test by using all valid digital inputs that are read from a local text file and writes its analog equivalent outputs to another local text file, so that for the post-test analysis, we can compare the input and output files side by side. Next slide, please. So this is just a breakdown of the post-test analysis and what occurs during the 2 test routines. So the 2 test routines mentioned in our previous slide read a 12-bit word from a DAC digital parameter file, which is the input file, and formats it to a 16-bit DAC 7311 digital data input signal by implementing the simple shift logic operator to make it go from 12 bits to 16 bits. Once the 16-bit digital signal is converted to an analog output, it's read by the oscilloscope tool and logged as a 12-bit digital voltage to an output file known as the DAC result file. The input file, DAC digital parameters, and the output file, DAC results file, are then compared to determine if the component failed or not. Next slide, please. So our test plan, the team's test plan is a summary of how the test routines and the post-test analysis are carried out. Initially, device under test functionality is verified using digitized 2 volts, 4 volts, and then 0 volts. If no error is logged when those voltages are sent out of the digital outputs of the analog discovery 2, then the device under test is exercised under all other voltage conditions by using a full range of digitized input voltages from 0 to 4 volts and then back down to 0, similar to what would appear as an analog sawtooth waveform when those values are converted. Then as those digital inputs are being converted to analog values, the software logs them to the output file so that it can be compared to the input file for the post-test analysis. And next slide. I'll go ahead and be giving it away to Edgar Palapa, who's gonna give you guys an overview of the work they did for the transmission lines.
Thank you, Marvin. Next slide, okay. Our hardware consists of 3 main components: the digital analog discovery 2, the 3 buffer boards to drive the 3 digital signals, and a digital to analog converter. The Digilent Analog Discovery 2 is a USB oscilloscope multifunction instrument that software team used to write JavaScript programs to generate specific digital words. The buffer boards were used as line drivers to drive digital signals across large cable lengths of up to 50 feet. Lastly, the DAC was used to convert the incoming digital words into analog signals. But more importantly, it was used as a device under test for radiation testing to see if radiation would cause the device to fail. Next slide, please. Here you see a transmission line block diagram with the 3 buffer boards and 3 transmission lines used to deliver the digital signals to the device under test. Before going into detail of the hardware, however, it's important to understand a little bit about transmission lines. Transmission lines are distributed capacitance, inductance, and resistance across a conductive medium. Collectively, these elements are known as the characteristic impedance of the transmission line. These elements cannot be removed since they are not physical elements. Nonetheless, they must be considered. When the device under test does not have the same impedance as the characteristic impedance, part of the incoming signal will be reflected back to the source. Thus, the original signal will become distorted because it will see some of that reflected signal down the transmission line. This is a problem for us because the signal at the DUT may send an incorrect digital word due to ambiguous digital logic levels. Thus, to solve this issue, proper termination was necessary. Termination is the practice of connecting a circuit that matches the characteristic impedance of the transmission line. So, based on the coaxial's characteristic impedance, only a 75 ohm resistor was placed in parallel with the DUT, necessary to match the coaxial cable's characteristic impedance. Next slide. Now that we have considered transmission lines and impedance matching, let's talk about the buffer board and why it is necessary for driving signals. For our application, the DAC needed to be at least 10 feet away to prevent radiation exposure to other nearby electronics devices. The DAC also needs 3.3 volts to operate, but when the DAC is 10 feet away, there is a voltage drop across that line. Therefore, we need 3 buffer boards to supply enough voltage to drive all 3 digital signals down the 10 feet of coaxial cable. Next slide. Now we'll pass it on to Brian Smith and Hugo Morales, who will talk about the device under test and the radiation test setup.
Awesome, thank you, Edgar. So for our device under test fixture, we used a DAC 7311, which is a 12-bit low power 50 megahertz component. The team decided to use this component due to its ease of use and simplified configuration. We implemented a dip socket into our brass board system, which allowed repetitive testing for multiple DUTs. Next slide, please. This is an overview of the team's design for our brass board system. We created a ground plane to reduce as much noise as possible and implemented 75 ohm resistors for impedance matching and bypass capacitors. A custom mount library was designed for the DUT, which consisted of creating a 15.24 millimeter wide mount and a 2.54 millimeter pitch. The team decided to use SMA connectors for the DUT signals for pins 1 through 3 and 6, which are sync, S-clock, digital input, and V out. As you can see from the side view, the SMA connectors were wired in such a way that they were going to be mounted on the back side to fit in our radiation chamber. Banana connectors were used since they are very common for testing purposes. Additionally, the team had to calculate appropriate trace widths for appropriate impedance matching as well. Next slide, please. This is a snapshot of our overall brass board design. As you can see, the 2 holes located on the bottom left of the back view are mounts for the banana connectors for the supply voltage and ground connector. The SMA connectors again were placed to be wired on the back of the brass board for wire distribution through the radiation chamber. Unfortunately, due to COVID-19, we were not able to order and test this for our overall project design. Next slide, please. And I will now pass this on to Hugo Morales to go over the test setup and DUT fixture assembly.
The radiation test setup helps us visualize why we chose the hardware components that were chosen. On the right, you can see the PC, which is used to control and power on the analog discovery 2, the AD2. As you can see, the wires have to travel a long distance through the radiation chamber, going through bends, and the 5-volt USB that the PC supplies to the AD2 is not enough to drive these signals. This is why we put the buffer boards to drive these 3 signals, which are sync, clock, and data. These signals then enter through the radiation chamber and connect to the backside of the PCB that Brian just mentioned. Next slide, please. Here you see the PCB board mount. This is used to mount the board onto the radiation chamber. You can see that we have the 6 outer holes on the right and left of the board. These are used to mount the actual mount onto the radiation chamber. The inner 4 holes that you see, one of them does not have a standoff. Those 4 holes are used to mount the actual PCB onto the mount. The 3-inch hole you see in the middle is used for space for all 6 wires to pass through. These 6 wires are the 3 that are coming in from the buffer boards, which are sync, data, and clock. The 2 wires which are required to power the deck, which are the +3 and ground, and the 6th wire being the V out, which goes back to the analog discovery to be then compared. In the middle, you see the assembled test fixture. The green part would be your PCB, and the gray part would be your PCB board mount. On the right, you're able to see the standoffs that we used in order to raise the PCB up a little bit to allow the user for any interface they need. For example, like connecting the SMA connectors or connecting the voltage. Next slide, please, and I'll pass it on to Mark.
Next slide, please. Overall, our team implemented a script to send out high-speed digital signals to the device under test. Again, the COVID-19 crisis held us back from finding a method of acquiring the analog signal from the output of the device under test. From a PCB standpoint, Brian was able to design the PCB, and Hugo and Edgar were able to design the PCB mounts. But again, the COVID-19 crisis, the COVID-19 crisis held us back from getting them ordered and manufactured because, well, manufacturers stopped receiving orders, and some of them were just really high priced. Next slide. And then overall, also, our team was also invited to the Aerospace Corporation's Microelectronics Reliability and Qualification Workshop, where we had the opportunity to present our project's progress back in February of this year. It was the first time in the workshop's history where undergraduate students participated in the event. And we were even featured in the March issue of the company's newsletter, which is off to the right. That pretty much concludes our presentation. Thank you to our company liaisons and to our advisor for helping us throughout this whole process and helping us make sure that this presentation was possible. Thank you. Next slide. And then questions.
Okay, thank you. It's a very interesting project. Sorry you weren't able to get everything done, but it looks like you got a lot done. So let's see, if there's a bunch of people in the audience. Does anybody have any questions?
This is Allison.
Go ahead.
So I would like to congratulate the team for what they were able to accomplish. And thank you, Anne, for hanging in there with them, and John. My question for the team is, I'd like to hear from each member the most important thing they got out of working on this project.
I'll go first. I think, I got a lot of important things out of this project. I think, what I got most out of it was being placed in a circumstance where I was able to, develop rapport with, industry professionals like you and John, and also with Anne, and, just learning how to take constructive feedback and then applying it to my work. And then also being able to develop rapport with my teammates to make sure that, this project got carried out, despite the whole events that have been going on. I think we're satisfied with what we ended up with. But overall, I think that's the most I got out of this experience.
I can go next. For me, what I got out of it was just, I feel like it was a great team dynamic, and we all learned a lot through this process. I was able to learn more about, PCB design and, implementing ground planes and trace widths for our signals, and just overall, the overall concept of what this project was all about. And unfortunately, we weren't able to do radiation testing, but to be able to almost get there was an achievement, I guess you can say.
I'll go next. I think what I got out of this project, what the most I got out of this project was throughout the testing. There's a lot that I didn't know that wasn't taught in traditional schoolwork. So this was definitely a great experience to learn about testing procedures like ohming something out, mastering the oscilloscope. I thought I had a good grasp on it before, but definitely after this, I really did learn a lot, and it opened my eyes to an entirely new field that I did not realize existed, which was reliability engineering, which is traditionally not taught in school. So I thought that was pretty neat.
I'll go next. So something that I learned doing this project is that obviously you're not gonna know everything like right off the bat, and thankfully we had liaisons and advisors to help us out and guide us through this project. And such, like Edgar was mentioning, a lot of like hardware features were introduced to us throughout this project, and not only hardware, but software itself. Throughout electrical engineering, we mostly learned C programming, but with the device we were using, which was the Analog Discovery 2, we got, at least for Marvin and myself and the other team members, we were introduced to a program called JavaScript, which none of us knew about. But with this project, it kind of forced us to learn, and that was something good that a new set of skill that gets us closer to like where we are now.
Okay, I'll go next. Well, I think I learned a lot of things throughout my senior design journey, but if I were to single out one of them, I would have to say that something I learned was being able to troubleshoot our design throughout the way. And this was mostly something that John and Anne helped me out with, because they would always ask something like, oh, well, what did you turn on first? Did you check this? Did you check that? I also learned how to do eye diagrams to check the signal integrity, which was something really cool because I had never even heard about that. Something else I learned was, how to cooperate with a group of engineers and, think about their opinion. So just think what they're saying, don't shoot them down for it, and just think, is it possible? Is it not possible? Let's try to figure it out. So yeah, that's what I learned.
Thank you.
Of course.
Yeah.
Thank you, Allison.
Other questions? So how close are you to this project being done? Would it be something that people could pick up and finish in 2 months or 4 months or 6 months? What do you think?
I think, in my opinion, because the main bottleneck of the project was the software. We were able to match the timing diagram that the DAC 7311, as like match it so that it has a valid serial write operation. I think with a little bit of guidance, I feel like we would have been done with our first prototype in maybe a month or so. The main issue we were having was mostly software because, like Lee said, it was a language that we were completely unfamiliar with, and we had to go out and actually talk to the Digilent engineers to ask them how to even start. But I think from my perspective, I think we're probably less than a month out from actually doing radiation tests with prototype 1, and then maybe doing some minor, debugging and troubleshooting to make sure that it was going to function when we would have taken it out for radiation testing. At least for this device under test. I know a couple things need to be changed for other devices, but our software showed that we're able to exercise any digital component or just any component that where you have to input a digital word or a digital signal into it. So
to tee off of what Marvin was saying, if the question is of continuing this project, well, we started off, our device under test was a DAC 7311, and that's just a digital to analog converter. And I know that the company liaisons were also considering, going further than that, being able to test A to D converters, our memories, our FPGAs, and, further other electronic components. So I think there's a lot of potential to continue this project as well.
Okay, thank you.
I have a comment, Mike.
Sure.
I think the team did very well in their preparation here and their presentation. One of the things that you asked that I think we should comment on is the handoff back to the customer and how well we are able to let the customer have a product that they aspire to back in August, right? And I think in terms of the hardware that I want to congratulate John and Allison. The hardware that they were able to provide the team was excellent in terms of them even starting back in the fall. One of the shortfalls was in the lab itself. We were up in, I think, the digital lab. I think especially Edgar and Hugo did fabulous troubleshooting, but boy, the test equipment, we were sometimes, hate to say, I think that we were sometimes troubleshooting the scope and the power supplies and the leads. And so that gives the students a lot of experience, but it did take away from troubleshooting the actual circuit. But anyway, but with all that said, they learned a lot. I would like to go back to, I think Lewis is still in control. I would like to go back to chart 22 because this is an important chart in terms of the handoff to aerospace. So one of the challenges here on this printed circuit board is it's a 2-layer board, and the bottom layer is a ground plane, and you always want a ground plane in terms of preventing ground loops and so forth in your design. But John from Aerospace challenged us because he wanted those connectors on the back. And if those connectors are on the front, this PCB design would have been fairly straightforward, but he wanted them on the back. And to put them on the back meant that the PCB design had to be customized quite a bit. And in that customization, that's why I was pushing the team to do this assembly drawing to show where the components are on the front and where they are in the back in terms of when Aerospace does go out and procure this board, that they would know how to assemble it. That's one thing. The second thing is, Brian alluded to it a little bit in his presentation, but if you look at the front view, the whole thing that Edgar said in his presentation part on the transmission line, which was excellent, is the termination of that transmission line to the resistors R1, R2, R3. And because they used a coaxial cable, they had common resistance within that line, which they had measured as 75 ohms. And that's why they had a termination of 75 ohms. So with John's help, helping with Brian, he came up with a way to design that connector, that SMA connector being mounted on the back to be able to have the ground of the outside of those pins going to the ground plane. But that center pole, which is the signal, he had it where it comes out to the front and that you would add a wire. And that wire is the W1, W2, and W3. And that's an important wire because it has to maintain that same resistance. So this drawing doesn't still need to be updated because there's a trace that Brian talked about that has to equal the 75 ohm as well as that wire. And so if we do the handoff properly, that is one thing I would say in terms of the aerospace people able to run with this design that would have to be corrected in the report. So, but this is so important, which we talk about a handoff, that it has to be complete in terms of the documentation so that the customer gets a qualified product. But the team, I think, interacted very well on this. They presented very well, and it's been an eventful year.
Thank you, Alan.
Thank you.
Thank you.
Thank you.
For the comment. Mike.
Yes.
I believe John Scarpula has a question, but he can't seem to communicate with the microphone.
So he did send me a question. He wrote it down. So let me read. This is from John Scarpula. What needs to be done to read back the analog output of the DAC into the test computer? How much difficulty would it be to obtain performance matrix like integral nonlinearity or effective number of bits?
It wouldn't be too complicated. Our initial approach was to use one of the interfaces within the Digilent software using the oscilloscope, and it has several tools where you could log the data for it. I'm not sure what its capabilities are as far as what was the term that you just mentioned, something linearity or something like that?
Integral nonlinearity?
INL.
I think Edgar.
You're talking about INL and DNL?
Yes, I can sort of comment on that. So that's I believe that's the curve between the analog output and the digital inputs. So I don't know if that's something that can be generated by the Digilent software, but we can definitely look into it.
Yeah, the oscilloscope tool offers several different panes. You know, you could extract voltage measurements, you could log them. There's all these different options that I was looking into once this whole crisis hit. A few of the things I was researching were that, just because, you know, that was kind of like our takeaway for the project was, okay, well, we got all the data control stuff out the way, you know, how could we have approached the data acquisition part of it? I don't know if that answers John's question, but I feel like our initial approach is probably the main starting point for extracting the information that he wishes to extract from the test.
Okay, I think we need to wrap it up. It's about time for the next presentation. Let me thank you all, thank all the audience for coming and participating. Thanks, Anne and the team, for the good work. Congratulations, and okay, stick around for the next meeting. I did put a link to the evaluation form in the chat, and you've got it in your announcement anyway. We certainly encourage everybody to log on and to Qualtrics and fill out a very short survey offering feedback to the students about how they did.
Dr. Thorburn, one quick question. I see that the presentation is being recorded. Is that going to be available to everyone, you know, soon, like in the coming weeks or something, for us to like?
That's the plan. We're working out the details of that, but that is the plan. Certainly, if you need a copy of it, we can make it available. Yeah.
Cool. Thank you.
Okay. All right. Thanks, everybody.
Likewise,
So the
thank
next presentation I think that I've seen some of the people log in. I haven't confirmed that everybody's here, but it's the Sarmiento brace problem. Is the student team here for that presentation?
Hey guys. Hey Dr. Thornburn.
Good afternoon, everybody.
Yeah, we're here.
All 5 of you? Okay.
Yep.
Excellent. All right. And I saw that your advisor is also here.
Looking for him in the chats.
Yeah,
I see him.
Everardo.
I see
Everardo, yeah.
I think I let him in a minute ago.
Oh.
Okay. Well, what we want you guys to do, I want one of the students to take command of the screen so that you're flipping through the charts. And we've got 40 minutes set aside. We're expecting a presentation that's about 20 minutes long, and then there'll be ample time for questions and discussion after the presentation. Do you have any questions before we get started?
Nope.
Okay.
Just grateful to be here. Yeah.
Okay. Well, we're glad to have you. So go ahead and then start. Thank you.
Hello, everyone. Thank you for being here. We are Team 23, and the title of our design is the Sarmiento Brace. We collaborate with UC Davis, Dr. Patrick Mitchler, not featured in the photo. Our advisor is Everardo Hernandez. He is featured in the middle of the photo. While our honorable mention, Dr. Chris Bachman, is not. I am positioned to the left. Kev Alonso is to my right. George Cepeda is in blue, and Colin Young to his right. Carlos Benavides to the furthest right. Here is our agenda. I will discuss the philosophy behind the design project. Then Kevin will head up the research, followed by Carlos and George with experimental methods. Colin will discuss the design, while the design analysis will be discussed by George. Lastly, I will follow up the summary. Enjoy. Some of you might be wondering, what is a Sarmiento brace? Well, then you have never broken your arm, and that's good. With this philosophy concept, I will discuss our problem statement and specifications that we developed. First, more context. This is the current treatment for a broken humerus. It is painful. By compressing the arm with Velcro, the patient is able to let gravity heal the bone back together. First, it requires some insight from the doctor to determine the adequate amount of pressure. Ultimately, the patient forgets and returns with a loose brace, making the whole process pointless because the bone heals incorrectly. Just a waste of time, thus requiring surgery. Ultimately, size restrictions are a big concern as a wider bite causes more probability of deformation. Here is our problem statement. The team shall develop a Sarmiento brace that will remain at correct compression as inflammation reduces with minimal to no intervention. As you can see from the diagram, this is the procedure, applying the brace after 7 to 10 days to encourage healing after it is straightened. Furthermore, the main requirement that we developed are the following. 1, one-handed application and removal. 2, improving the tensioning system with respect to the reduction in inflammation, ideally auto-tensioning. 3, radiolucent materials. That means no metals blocking the x-rays in front of the break. Now, the Meyer specifications was addressed in the following in no order. A, modularity for different types of arms. B, tuberosity pressure, which is a point on the arm that could help with counteracting the moment arm that causes the deformation in the healing process. And C, healing with those acceptable deformation angles, which we'll talk about, which are called the varus and sagittal plane angulations. Okay, perfect. Now you might understand the importance of this project, as is a lot of time and money can be saved by improving the Sarmiento brace. Now I'll pass it on to Kevin, who will discuss the research that was required to develop criteria to design the brace around.
All right, thank you, Nick. So before we begin our design process, we wanted to learn more about what a humerus fracture is, how the anatomy of the human arm and interactions can affect the design. Therefore, these 3 subjects of the arm shown are what we will focus on for research. We'll begin by going over the main points. I'll be going over what the humerus bone is, the significance of the varus and sagittal angles, the ideal fracture type and location for our design, all related factors we considered for the design process, and how we had originally intended to validate our brace design. Carlos will then describe the muscles, arteries, veins surrounding the humerus bone, and the bone reformation process. So if we go on to the next slide, the humerus bone slide is not one of the larger bones of the upper body region, located between the elbow joint and the shoulder joint. The average length of this bone can range from 9.5 inches to 13 inches, but can also differ by gender, as seen on the table. Injury to this bone is caused by trauma, such as car accidents, sports injuries, falling down a set of stairs, and can result in pain, deformation, bruising, swelling of the muscles and bone, and can cause possible nerval damage. We want to take these different humerus lengths and the symptoms as factors to improve the current brace design that is given to us. Now we're going to get into the varus angle. As shown on the left figure, the varus angle is a deformation of the humerus bone to its normal axis. It's caused by humerus fracture and can result in a deformation shown to the figure on the right. A larger deformation means that the fracture would not be suitable for brace treatment. And according to clinical studies, most brace treatments have a higher success rate on humerus fractures that have a varus deformation of less than 20 degrees, with a successful healing average of 13 degrees. Another angle to consider for our design is the sagittal plane angle, which is normal to the coronal plane as shown on the figure. Fixation failures can cause a reduction or loss of elbow flexion, meaning that the patient will not be able to move their arms as well before the fracture. From clinical trials, the average extreme sagittal angle for the brace treatment is 12 degrees, which means that any greater angle will result in a consideration for bone planing surgery, which is a pretty expensive procedure. A humerus bone fracture is categorized in 3 different locations: the proximal, the midshaft, and the distal. The proximal is a position closer to the shoulder, the midshaft position is centered to the region of the bone, and the distal position is closer to the elbow. From case studies, the proximal and the distal regions have lower success rates because they are more difficult to reach with a brace. There are muscles and connecting bone joints in these regions, and many of these treatments undergo further bone planing surgery in the end. However, the midshaft is not surrounded by bones, so it's not surrounded by any muscles or anything like that, so it's easier for a brace to access the region. 5 different fracture types are shown on the figure to the left, classified as either types A, B, or C. From clinical trials, the type A simple transverse fracture is the most successful fix with the Sarmiento brace in comparison with the rest of the fracture types, as shown on the data. This is because the types B and C fractures are complex fracture types with multiple bone fragments, which make it difficult to heal with the brace. Even the type A oblique fracture is not considerable since gravity is involved in the healing process, and the angle can cause a displacement in the reformed bone. Since the purpose of the brace is to apply pressure on the bone region to enhance bone reformation, the transverse fracture type A is the most ideal fracture for a successful process. Therefore, our design will focus on the type A transverse fracture on the midshaft location in order to enhance the success rate, maintain the compression concept, but also take humerus inflammation into consideration, and increase the comfortability of patients since these braces are applied onto the arm for a range of from 5 weeks up to 20 weeks after the fracture. Lastly, we were discussing with our liaison about the use of a cadaver to validate our brace design to the target value shown on the text at the bottom, with an actual deformed arm. But that won't happen anymore because of the current pandemic circumstances. And so now I'll be passing on the presentation to Carlos, who will be discussing more about the muscles and inner arteries.
Everyone, I'm Carlos. So when you first break your humerus, aside from different breakage types, you also have open and closed fractures. And open is being when the bone literally comes out of your skin and is outside your body. And typically open fractures are displaced, which means that the bones still somewhat line up, and the alternative to this is non-displaced. This means that the bone still lines up somewhat together. So if you could imagine, an open fracture is more likely to require surgery than a closed fracture. And a closed fracture is what we're aiming for our brace to target. So when you break your humerus, your bone is not just kind of hanging outside your body left and right. You have your biceps muscle, your triceps muscle, you have soft tissue, you have tendons, you have all these things keeping your humerus bones together. And the goal for a brace is to keep the muscle, the bone, and all the soft tissue around the arm close together in order to facilitate the body's healing process, which is what I'll go over in the next slide. So when you first break your humerus, you have inflammation not only due to the break itself and the veins inside the bone rupturing, but also due to your arteries carrying the necessary nutrients to your humerus in order to start the healing process. So as time goes by, your bones start connecting together via calluses that are formed by the cells inside your body. And inside these calluses, you have also different cells, and these include osteoblasts, which are in charge of dissolving the bone fragments. You have osteoblasts, which create new bone, and you have osteocytes, which live inside the bone. And these calluses become spongy, as you can see when you first break your humerus. And figure A, the bone is separated, you have a blood clot, the bone starts to come together. In picture B, you start forming these calluses in picture C. And by picture D, that's when your bone is fully healed. So it's important to keep the bone together so that you don't have any gaps once your bone is healed and it doesn't end up growing longer than it should be. And on the next slide, I'll go over some more important stuff. So one thing we took into account was the brachial artery. So it's important to take into account this artery because it carries blood from the heart into the body, but you also have veins which carry blood from your body back into your heart. So we don't want to create a brace that's too tight that's going to restrict the blood flow, because then everything I just talked about is not really going to work. You're not going to have blood flow, you're not going to have proper healing, and you might even develop other complications. And on our next. So now I'll talk about our experimental methods. So we wanted to get a numerical value that we could use in order to design our brace. In order to do that, we used a blood pressure monitor, which we tested on all of us. And the way a blood pressure monitor works is that when you put it on, this inflatable cuffs inflate to the point where they squeeze your arm and it starts cutting blood flow from the arteries. And this creates a vibration that's detected by the meter. This is called your systolic blood pressure. And as the cuff relaxes, you get a diastolic reading. So what we did is we placed an FSR, and then we placed the cuff, and then we started the process, and we got our systolic blood pressure reading, which is the point of blood restriction. And we designed our brace to be less than that in order to avoid restricting blood. In order to come up with a numerical value, and for the sake of calculations, we didn't use the arm, we used cylinders because we wanted to prove some formulas to see if we could apply constant pressure no matter what radius we use. And as you can see here in this slide, we have George, which is holding a cylinder, and Colin, which is using a white little strip. This was our testing method, which is something I'll go over more in detail in the next slide. So the FSR I talked about is a force-sensitive resistor. And the way these works is that these resistors come with a set resistance that we use in order to get a force reading. And we program them using an Arduino board and using a voltage divider. So as the FSR resistance goes down, you get a force reading. So when you press on it, you get a certain resistance value that corresponds to a force reading that we use in order to do some calculations. Next slide. So the strip that you guys saw earlier in the previous slide is just a paper strip, and then we created it with yarn and some wood sticks. We wanted to prove that we could get constant pressure around the arm, which this case was a cylinder that we use no matter what radius you use, because when you first break your humerus, you have inflammation, so your arm gets bigger, and as time goes by, inflammation reduction occurs, which your arm gets smaller because you don't have as much blood flowing into the arm. We want to prove that we can get a constant pressure no matter what radius you use. The radiuses being different sizes of arms. Some people have smaller arms, some people have bigger arms. And on our next. So the way we did it, as you could see the previous slide, we have this circle which resembles the cylinder, and we place the FSR in 3 different positions, and we use 4 different cylinders of 4 different sizes. So if you guys remember, I said I placed the FSR inside the pressure cuff. So the reading that most of us got was 50 newtons. So at 50 newtons, that's when the blood pressure monitor started to cut off blood flow. So that's what we wanted to target our brace around, to be less than that, to prevent blood flow restriction. And now I'll pass it on to George, who will discuss our results.
Thank you, Carlos. So let us move on to our actual testing results. As you can see in figure 17, we tested 4 different radii to validate our formula. The force is equal to the pressure times the radius of the cylinder times the length. And it's pretty much derived from the equations for tangential stress in thin-walled cylinders and general normal stress, which is the stress is equal to the force over the area. As you can see from the left to the right, we start off with huge radii and ended up with small radii. Keep in mind that the brace is intended to support people with large arms and people with skinny arms like mine. I wish I can show you all how scrawny my arms look, but due to unfortunate circumstances with my camera, I can't. But anyway, in the figure, we also concluded that the radius increases, as so does the force as well. Next slide, please. So moving onward to our cylinder test results, we tested all 4 different radii, and it turns out that the second position of the FSR gave us closer values to our desired target force, which was 50 newtons. The second radius and the third radius have more error than the first radius and the fourth radius, but they're still reasonably close to the 50 Newton target. Positions 1 and 3 for all radii showed much higher FSR readings due to the stress concentrations caused by the glued joint between the yarn and the laminated paper for the test apparatus. Next slide, please. The required force to achieve the theoretical FSR reading of 50 newtons or any other constant FSR force increases linearly with the cylinder radius as shown in the figure. At all 4 radii tests for position 2, the experimental FSR readings were reasonably close to the theoretical FSR readings overall. The linear relationship between the required applied force and the cylinder radius is important because the applied force can be provided by a spring, which has a linear force displacement relationship due to Hooke's law. Now I'll go over the experiments we conducted to quantify the pressures experienced under the standard Sarmiento brace. The diagram on the PowerPoint slide just shows the FSR positions underneath the brace. Position 2 faces on the arm, whereas position 4 faces towards the rib cage. Next slide, please. The 3 test subjects tightened the brace over their arms without any assistance. The average pressure across all positions and all test subjects turned out to be 4.22 psi. However, the highest test subject across was 5.15 psi, which may prove to be a better pressure target for the improved brace, as our liaison, Dr. Patrick Mitchler, suggested that the tighter the better. And now I would like to pass it on to my team member, Colin, and he's going to describe the components of the brace and the design for our final prototype.
Thank you, George. Hello, everyone. I'm Colin, and I will be going over the design we came up with. I'll first explain how the design works with an exploded view of the assembly. I'll go over the crank spool and the significance of the gear ratio contained within. I'll discuss the mainspring buckle design and the mainspring tests and results. Then I'll talk about the changes made for the final prototype. And finally, I will discuss how the design can be improved in the future. Next slide. The design can be summarized into 2 systems. The tensioning system encompasses the mainspring, worm and spur gear mechanism, and the crank spool. The preloaded mainspring exerts force on the crank spool, directing the force tangentially onto the brace, which adjusts its circumference to accommodate inflammation reduction. The ratio of force and surface area stays constant throughout inflammation reduction to maintain constant pressure on the broken arm. And the worm and spur gear is used to set the initial spring displacement according to the initial circumference of the arm. The ratcheting system is used to wind up and lock the brace at maximum circumference, making it easy to slip the brace over the arm, after which the ratchet can be released, freeing the brace to contract over the fracture. Next slide. Here's the crank spool design shown in figure 24. It contains a 1:4 gear ratio, which minimizes the spring deflection required and maximizes the range of brace contraction, making for a compact assembly. 1/4 of the spring force is transmitted to the spool to tension the brace. And in addition, the ratchet gear locks with the crank spool to allow the tensioning system to be locked. Figure 25 shows the buckle design for the mainspring. The buckle fastens the cord to the rubber mainspring effectively, which was a major challenge for the design. The slot has smaller dimensions in the cross-section of the rubber to ensure a tight fit, but it is necessary to stretch the rubber to thread it through the slot to complete the assembly. Next slide. After creating the spring, we tested it by hanging weights on one end and measuring its displacement. We also waited 10 minutes to allow any generated heat to escape the rubber, which affects the spring displacement and represents the condition of the brace in practice. Next slide. Plotting force against displacement yielded a nonlinear section followed by a linear section. The spring constant of the linear section came out to be around 3.4 pounds per inch. And the x-intercept of the best fit line represents a sort of emulated spring displacement, which must be subtracted from the required spring displacement of a perfectly linear spring to determine the actual spring displacement required for the rubber spring. Next slide. Here's the final prototype shown in figure 28. It's designed only to validate constant pressure over different circumference cylinders without changing the initial spring displacement setting. The largest spring that could fit inside the housing was too weak to produce a good reading on the FSR sensor, so the brace was shortened to increase pressure by decreasing the brace surface area. Next slide. Figure 28 is a photograph of the manufactured and assembled prototype, while figure 30 shows a close-up view of the ratcheting system. While we tested the prototype, we found that parts inside the housing were in contact, and this produced substantial friction that prevented the brace from working properly on its own. Because we couldn't do anything about this, we had to overcome this obstacle by manually assisting the brace by tightening it over the cylinder until the FSR sensor reported force values well above the theoretical reading of 10.17 newtons. And upon releasing the brace, the FSR consistently settled on 10 to 11 newtons on all tested cylinders. While this seems promising, these results should be taken with a grain of salt, as we had to manually assist the mechanism in order to overcome internal friction. Better design and more tests are needed to reliably verify that the concept works. With the current gear ratio, the design would require very large forces and a very large spring to apply the pressure target of 5.15 psi over the whole arm. Figure 33 shows that the current 1:4 gear ratio requires a whopping 350 pounds. For future design iterations, a larger gear ratio is necessary to decrease the force and spring constant requirements at the cost of greater required spring displacement. And that concludes the design portion of this presentation, and I will now hand it off to George, who will be discussing some of the design analysis.
Thank you, Colin. I'm going to explicate the design analysis for our crank spool, and we use something called finite element analysis. Some of you may ask, what is FEA? FEA is pretty much a program that helps us predict how an object will react to forces, heat, and vibration, and many other things. It helps us determine whether the object will break, wear out, or work the way that we want it to. And in this case, our design has to support a load of 50 pounds, and knowing me, I can't lift 50 pounds with one arm. That's really heavy. It's quite heavy to think about, but we want the design to support this load. And our design needs to support a torque of 12.5 inch-pounds. And some of you guys may know what torque is, but torque just describes a measure of how much a force acting on an object causes the object to rotate. In this case, the torque will take place in the crank spool when the Kevlar string that we utilize is rotating the spool, so the brace is just adjusting to the appropriate circumference size of the arm. Moving onward, as mentioned previously, we utilize FEA in SolidWorks to show how or exactly our design will yield, and the crank spool will not permanently deform at a large magnitude with applied loads. Looking back in the figure, it may seem overwhelming, or some of you may not even know what's going on, but I'm just going to summarize it all. When the load is being applied, it did not significantly affect the displacement of the spool, and the largest displacement is less than 1/1000th of an inch, which is negligible. And based off our results, our design would not work. Based off our design, it would work the way we want it to, and that's a good thing. I would like to pass it on to my team member, Nick, to finish us off with the summary and bill of materials.
Hello, and I'm back. Thanks for listening. Now, in summary, here's the loading of the brace in action. Colin is pre-stretching the rubber spring to actuate the tension system prior to applying the brace for tensioning. Now, to get some perspective on how much it will cost to manufacture, here's the bill of materials. This is important as it provides an estimated cost of about $97. Considering overhead would be about 5 times the current cost per part. So in comparison to the standard in the market, it is expected to be less expensive by nearly $20. Then there's also the tension system, which is improved using Kevlar instead of Velcro, which is more ergonomic in comparison to the noisy Velcro that straps across the body, restricting the movement. The improved brace adjusts to inflammation while maintaining constant pressure on the arm. Since the brace is one piece, it coils around the arm. The torsional stresses will actually be reduced while providing comfort to the patient. So in conclusion, we'd like to thank Dr. Thornburn for his dedication for providing us with the opportunity to present our project and giving us the professional development to go out into the world. Thank you. For Dr. Bachman for coordinating the amazing project. It's been a lot of fun. Thank you. Dr. Patrick Mitchler for giving us the expertise to ensure we're doing the right thing along the way. And thank you. And Professor Hernandez for keeping us, or Everardo, for keeping us accountable and organized. Super important. Thank you. Lastly, Cal State LA, ECST, and the Makerspace team for helping us make this idea a reality. We are just joking about the no questions. Please, all questions are much appreciated. I'm going to flip to our references while everyone gathers their thoughts. Thank you.
Okay. Thanks, team. It was a very interesting presentation.
Thank you.
Questions?
I have a question.
Go ahead.
Would this work on another part of the body or just the arm?
Theoretically, it could work on, well, technically just the arm because the Sarmiento is only used with gravity. Other parts of the body, maybe a finger. I'm not sure. What do you think, Colin?
Well, more research on the physiology of other body parts would need to be done in order to verify that.
I see.
But theoretically, this tensioning system could be applied to any other brace for any other body part, I suppose.
I would like to add on to what Colin said. We also have to study the biomechanics behind like different limbs because, our different limbs have different types of range of motion, and we kind of need to know what that is in order to accommodate that in our, design.
Yeah, I also wanted to add in, there are certain braces out there that are manufacturable and designed for, let's say, like a leg fracture, like on the fiber and stuff like that. There are braces out there. The only concern is that the structure, the anatomy of the body is different from on the leg in comparison to the arm. So our main target was mainly the humerus bone of on the upper body region. So there are possible cases that would just have to be more research done for other bone regions of the body.
Thank you. Good question.
Thank you very much. I appreciate it. I broke my wrist, so I was wondering if that could work. My wrist is now, after 2 years, I've got a big bump there from it.
Thank you. Maybe
it's
hopefully.
a great design, guys. Thank you very much. I appreciate it.
Thank you for your kind words.
I wanted to follow up with that question a little bit. When I think about the difference between an arm and a leg is often in compression, right? Because it's supporting the weight of a person. So unless they're sitting down, would this sort of brace provide enough support that you could actually handle something that might be in compression?
That's a very good question indeed. That's outside the scope of this project, but maybe we'd have to do a
If
lot
you're
of
bedridden, yeah. Yeah, I think as long as you keep the leg elevated, maybe. But yeah, Colin's more safe with that answer. Thanks.
maybe
man.
after like 10 years of research and development, there'll be like a new project, universal tensioning system for all braces, and they can tackle it.
I like it.
Other questions?
So I have a question. So it seems like you guys came up with a pretty cool prototype, and a lot of aspects of it worked, and it seems like some aspects though didn't work. What would be kind of your team's next step to, I think, put this on a person and get into some clinical trials? What would you have to change about the mechanical design?
Well, first and foremost, we'd have to change to a larger gear ratio. So that would reduce the force requirements needed to tension the brace. But that would also increase spring displacement requirements, and then the whole assembly would be a lot larger in that regard. Second, the parts that didn't work in the prototype were that a lot of the cords that came out of the spool crisscrossed with the mainspring, and there just wasn't enough space for both of them to clear without touching, and that friction prevented it from working properly. So we'd have to rearrange some of the parts inside the assembly in order to ensure that they won't crisscross and no internal friction issues would arise. But
Also, yeah, go on.
I don't think it would be too difficult to figure that out, though. I think most of the work done, most of the work is already done, in my opinion.
Yeah, and definitely we had some suggestions about changing the spring mechanism to a different type of rubber, to rubber tubing, which could have more surface area and less space.
Right, and also be able to be directed with pulleys, so
Mhm.
it can be folded within the assembly to make it even more compact. Yeah, I hope that answers your question.
No, that's cool. So it sounds like you haven't given up on the design, just a little bit taller, a little bit stronger springs. You'll be in the zone.
Exactly.
Cool. Very cool. All right. Good. Yeah. Good work, team. Very, very impressed with, seems like you got your whole team there working and getting stuff done, and very impressed with everyone. Good job.
Thank you.
Thank you, Dr. Bachman.
Thank you. Other questions?
I just want to add, everybody worked really hard and they did a very good job. Excellent job to me. I mean, regardless of what the situation, is of COVID-19, these guys really work really hard. Even like coming in or working extra to put the prototype together just to prove the concept. Congratulations, guys.
Thank you, Professor Alvarado.
Very good job.
Thank you very much.
Well, couldn't have done it without you.
Yeah.
Really grateful.
Thanks. Yeah.
Congratulations, everyone. It was fabulous.
Thank you so
Thank
much
you
for
so
your
much.
words.
Thanks, Mom.
Okay. Okay, well then, let me thank you all for coming today. I appreciate it. This is the last electrical and mechanical engineering presentation for the day, but we've got a full plate or a full schedule of presentations tomorrow from 2 until 6. There are also computer science, civil engineering, and technology sessions. We've still got another 7 days of the Expo. Please participate. It's good for your classmates, for your students. I want to thank all of the clients and external people that showed up for the meeting. Okay, don't forget to fill out the evaluation form.
Thank you so much, Dr. Thornburn.
Okay. Okay then, well, signing off. Congratulations, guys. You did a good job.
Thank you for everything.
Thanks again.
Thank you. Bye, guys. Good job.
Bye.
Thank you, Eduardo, for everything and for pushing us. Helped us a lot.
I had to. That's my job. Thank you, Michael. Thank you, Chris, if you're still around. And I'll see you around.
So long.